Assalamualaikum to our respected lecturers. We are group I1 and today we will be presenting our integrated design project for the subject CFB 2053 Reaction Engineering 1 and CFB 2063 Separation Process 2. The title of our project is Production of Nitric Oxide. In this video, we will explain the chemical reaction process to produce nitric oxide, the selection of the best reactor and separation system, strategies to maximize NO yield and minimize side product like NO2 and reacted ammonia, and finally how we ensure a high purity NO output suitable for medical use, along with a clear justification for each design choice. Here is our group member. Today I will be presenting an overview of nitric oxide production process, particularly focusing on producing high purity nitric oxide for medical application. Our main goal is to produce high purity nitric oxide, which is widely used in medical applications such as treating respiratory issues and pulmonary hypertension. Since it's used in the human body, the purity of NO is absolutely critical. The process begins with catalytic oxidation of ammonia. This means we use a catalyst to speed up the reaction between ammonia and oxygen to form NO. There are two main reactions involved. The primary reaction is ammonia and oxygen producing nitric oxide and water. However, there are also a side reaction, which is nitric oxide and oxygen producing the nitrogen dioxide, which is an impurity we don't want in the final product. During the reaction, impurities are formed. These include nitrogen dioxide, which comes from NO reacting with the excess oxygen, and unreacted ammonia, which must also be removed. These impurities can reduce the quality and safety of the final product. After the reaction takes place in the reactor, the mixture of NO, water, and impurities goes through a separation system. This system removes the water and unwanted gases, ensuring we get pure NO as the final output. Lastly, I want to emphasize that for medical grade nitric oxide, purity is extremely important. Even small traces of impurities like NO2 can be harmful when inhaled by patients. That's why the separation and purification step is crucial. In summary, producing nitric oxide for medical use involves carefully controlling the catalytic oxidation of ammonia and truly purifying the product to ensure it's safe and effective.
For our reactor system, we have selected a packed bed reactor or a PBR. PBRs are the best choice for this process because they provide efficient heat transfer, excellent gas to solid contact, and a compact design suitable for high temperature operations. To achieve 98.01 conversion of NH3, we require 1138.66 kilograms of a platinum rhodium catalyst. This design ensures a maximum efficiency in producing high purity nitric oxide. For our purification system, we used a two-step process to achieve 99.9% pure nitric oxide. First, we remove water using a phase separator. Since water has the highest boiling point among the gas mixture components, we use the stream between 21 and 100 degrees Celsius using refrigerant R3148. This condenses the water into liquid form, which is then removed. Next, we use an adsorption column. The gas mixture passes through a packed bed absorption column filled with activated carbon and silica gel. The activated carbon removes nitrogen dioxide, hydrocarbons, and residual moisture. The silica gel ensures the complete removal of water and trace NO2. By combining these methods, we achieve ultra-pure nitric oxide that meets the stringent standards required for medical applications.
To maximize NO production, we focus on three main conditions specifically when the reactions occur at the reactor. Firstly, optimal temperature. The catalytic oxidation of ammonia operates most efficiently at around 800 degrees Celsius, and this temperature provides sufficient energy to drive the reaction forward, ensuring the high conversion rate of ammonia to nitric oxide while also minimizing the formation of unwanted byproducts like nitrogen dioxide. Next, pressure control. The reaction will maintain at a high pressure, which is approximately 500 kPa, to increase the reactant concentration in reactors as well as improve the reaction kinetics and produce higher product yield. making the process more efficient without compromising safety. Last but not least, catalyst efficiency. Based on our design calculation, approximately 1,138.66 kg of catalyst is required in the packed bed reactor. This quantity ensures sufficient surface area and contact time for the reactants, allowing the ammonia to be converted efficiently into nitric oxide. By providing optimal catalytic condition, we are able to achieve a conversion rate of 98.01%, which significantly enhance the yield of NO while minimizing unreacted ammonia and side reaction. These strategies ensure the efficient and consistent operation of the process, resulting in high yields of NO production.
So now we are going to discuss how to minimize the byproduct. Since we are going to produce NO, further oxidations may occur in these reactions that may lead to the NO2 formations. So now we are going to discuss how to reduce the NO2, which is the byproduct. First, we can minimize the NO2 formations at the reaction state. How? We can optimize the O2 feed, which we calculate the amount of the O2 needed in these reactions, and then we put the exact amount of O2 in the feed so that there is not too much excess O2 in these reactions that may lead to the further oxidations that may produce NO2, which is the byproduct. Second one, we can rapid cooling after the reactor to avoid post-reactor NO oxidation, because oxidation may occur in high temperature. The second one is how we design the adsorption column. So, to remove NO2, we can use the absorbents with high affinity for NO2 but minimal affinity for NO, so that more NO2 will be absorbed and removed in these reactions. In our case, we use activated carbons and silica as an adsorbent. And also, for the absorbent conditions, we can use the lower temperature in the column. Generally will help absorption of NO2, which is NO2 will diffuse and will be absorbed, so it will be removed more NO2 in this case. And the third one is operating condition of the adsorption column, which is we can use the low oxidation partial pressure in the gas entering the column that may reduce the further NO2 formation inside the column. And the second one is we're going to use the proper column sizing, which is larger contact times. Why? Because if there is larger contact time, so more NO2 will be diffused and absorbed, so more NO2, which is the byproduct, will be removed in this case.
Since nitric oxide NO is our target product, other compounds in the chemical equation can be considered as impurities, which are water, H2O, as the largest impurity contributor. Next, we have O2, oxygen, nitrogen dioxide, NO2, and unreacted ammonia, NH3. So, how do we remove these impurities from the stream to achieve 99.9% purity of nitric oxide? First, we will use a phase separator that will operate at around 25 degrees Celsius to separate water from the gas stream in liquid phase. At this step, most water can be removed, as at 25 degrees Celsius, only water is in liquid phase and other compounds are in gas phase. This step is crucial since we know that water is the major contributor to the impurity content. Next, we will use adsorption column with activated carbon as the adsorbent to remove most of the nitrogen dioxide, unreacted ammonia, and residual water content in the stream. Activated carbon is highly effective due to its large surface area and strong adsorption capacity, allowing these unwanted components to be efficiently captured. However, some moisture and trace amounts of NO2 may still remain after this step. To ensure complete removal, we will use silica gel as the final adsorbent layer. Silica gel has a strong affinity for water, effectively capturing any remaining moisture while also helping to eliminate the last traces of nitrogen dioxide. By implementing this two-stage adsorption process, we can significantly improve the purity of the final gas stream, ensuring the highest purity of nitric oxide.
That is all from us. Thank you.